So let's continue on our minimizing total tardiness problem on a single machine. Okay, in a feasible schedule, job I can be either before or after job J. Okay, so we need to allow our program to have these two possibilities. So if job I is before job J, this is a condition we need to have, right? Cj must be greater than or equal to Ci plus Pj. What does that mean? This is the completion time of I. I is before J. So the quickest way to finish job J is to start job J right after the completion of Ci. Okay? And then you really need Ci plus Pj to complete your job J. That's the case when job I is before job J. Alternatively, you can put job J to before job I. Okay, so you need to satisfy either this or that. You cannot put both of them into your program because then you get infeasible, an infeasible program. So you need to satisfy either or. The good news is that you know how to deal with either or at least one of the constraints. So let's use Zij as a binary variable to control the selection of these two guys. Okay, so you can see this is a very familiar either or constraint with a binary variable. We say Zij is 1 if job J is before job I, or 0 otherwise with these two constraints. Then if Zij is 1, okay, then this constraint is redundant. And then here you have 0 as your right hand side. So that just means you need Ci to be greater than or equal to Cj plus Pi. Okay, exactly what you need. Or if Zij is 0, then it's the reverse thing. The remaining thing is that you need to decide what's a good or appropriate value of m. If you observe the left hand side, you know m must be an upper bound of your left hand side. Okay. It seems to us that Ci minus Cj or Cj minus Ci is talking about the difference between completion times. And if you think about what's the largest possible difference between completion times, seems to have some relationship with the total total processing times, right? So ask yourself whether the total processing time is a good, is an appropriate, is an okay value for m. Okay? If not, then try to modify it a little bit. Okay, so the last thing we need to do is to linearize our objective function. We want to minimize total tardiness. Okay, a maximum function, of course, is not okay for our linear integer program. And again, this is not difficult for you. You know how to deal with it. Let's replace it by the tardiness variable tj. Then tj as a maximum in a minimum function. All we need to do is to let tj to be greater than or equal to the first term, and then for tj to be greater than or equal to the second term. Also, the non-negativity plays a role here. Once you have this, then you include the two set of constraints we talk about to select either this or that. And of course, Cj should also be non-negative for all the jobs, and Zij should be 0 or 1. So with this complete formulation, you can minimize the total tardiness on a single machine. Okay? Again, if the problem scale is not too large, then MPO solves it. If the problem is somewhat too large, then you need to do something else. Let me give you another example. It's about minimizing make span on the parallel machines. Okay, so now you have multiple machines. You have n jobs, and you have m parallel machines. Okay, parallel machines. your job has processing time pj. Now you don't care about due date or whatever because you are talking about make span. Okay, and let's assume the capacity of each machine is unlimited. So machines are the same and unlimited. One thing that we did not tell you is that when we say that job J has processing time Pj instead of Pij, that means all the machines are identical. Okay, all the machines are identical. It's not that when we put job 1 to machine 1 or machine 2, we get different processing time. Oh, no. Okay, all the machines are identical. A job can be processed at any machine. Processed at any machine. However, it can be processed only on one machine at a time. So on each machine, it's still serial production. It's just that we now have multiple machines. Okay, so we have multiple machines. So just like the graph that you have already seen. One possible schedule is something like this. Okay, at the beginning we work on 2 jobs at the same time. When you finish one job, you can start another job on that particular machine. And if you look at these 2 machines separately, each of them is just a single machine, single serial machine. Okay, and the jobs have no relationship between each other. They are all independent. All we care is the turn point here when all jobs are finished. Okay, that's our make span. Different schedule give these jobs different completion time Cj, and if you have Cj, then the make span would be the maximum of Cj. Okay, so the problem would be to minimize your make span by scheduling all those jobs onto your multiple machines. One key observation here is as long as you put some jobs onto a machine, then the sequence there would not matter. Okay? In the previous problem, the sequence matters because you have due dates. But here, the sequence does not matter because you only care about the final completion time. So the problem is really to just assign jobs to machines. Okay? In some sense, this is an assignment problem. It's not the assignment problem in network flow, but the scheduling problem is just an assignment problem. You need to decide. Whether you want to assign job J to machine I, okay, or you want to do something else. Each job must be assigned to at least one machine, and that's going to make Xij 1. On machine I, for each machine, we want to know what's the last completion time. Okay, and if you are talking about machine I, then you know for some of the j's, Xij would be 1. That's the set of jobs assigned to that particular machine. Then the total processing time or the last completion time on that machine would just be this summation, right? Then your objective would be to minimize the maximum of these total completion times. Okay, just like the graph we showed to you. If this is machine 1, this is machine 2, and this is machine 3, then how do we know how long each bar is? It must be the jobs, the total processing times of those jobs assigned to that particular machine. Okay, so for each I, you have a number, the final completion time, and your make span would just be the maximum among all the jobs. Maximum among all the machines. Okay, so seems not to be hard. All we need to do is to linearize it, right? And again, you know how to do it. It's just a maximum of a few terms inside a minimization objective function. So all you need to do is to minimize a new variable m, subject to that m is at least each term. Okay, m is greater than or equal to each term, and xij must be non-negative. Of course, you know one constraint again is missing, is that for each job, you need to assign it to at least one machine. Okay, in this case, you can assign it to exactly one machine. That's good enough. So let's complete this. Okay, among all the machines, one must be used to schedule that job. That's something you need. And once you have that, then you're done. Sometimes people want to do a somewhat different thing. They want to maximize the completion time of the least loaded machine. Okay, so all the machines have different workloads. And now we want to maximize the completion time of the least loaded machine. Seems to be a weird condition, but sometimes we want to do that for example, fairness. Okay, we want to somewhat balance the workload of all the machines or all the workers, and the way to represent fairness sometimes is to say that hey, everybody is so busy. Okay, and even the least loaded one is still having a lot of jobs. Okay, anyway, if you want to do that, then the problem is not a big deal. You just change min to max and then less than to greater than to less than. Okay, then you really have that problem. One interesting thing is that for this formulation, you don't really need this assignment constraint. Okay, because you definitely want to assign jobs so that you can increase your capital M. Okay, so that may be a difference. Okay, so that's about scheduling. We gave you two examples, one with a single machine with due dates, the other one with multiple machines with max span. Okay, there are obviously many more, but all you want to do is to use integer programming as your tool to formulate to deal with all those problems. Thank you.